Guess that may as well make a start. So can I say welcome everyone and thank you for coming along today. Hello Sylvie.
Just on time?
Just on time. Timed it perfectly. So my name's Lachlan McGinness. I'm a PhD student here in the School of Computing, and I am going to be giving a talk about some of the work I've done with my PhD research. So I guess the other thing I'll just quickly say is, unfortunately, I didn't have enough time to cut down the slides, so it's very long, so I'm going to move relatively quickly. But if you want, feel free to just interrupt and ask a question as we go if I go through something too fast. Is that okay to everyone? All right. So I'll just start by acknowledging the traditional owners of the lands that we're meeting on today. So very quickly, this is me, and this is my supervisor, Peter, who's just here. Yep, and I'll just keep moving. So today there's, I guess, kind of 6 sections. I'm going to start with an introduction, then I'm going to go through some different parts of different things I've been working on my PhD, and then finally I'll do a quick wrap up at the end. So let's just dive straight into it. So the motivation behind my PhD is that there are many teachers across Australia who are getting overworked and burning out. So according to the Australian Institute for Teaching and School Leadership, the proportion of teachers who plan to leave the profession is close to 35%. So it's very high, and it's been high ever since the pandemic. And the number one factor that's influencing teachers in this decision is workload. And then there was a report done by the Teachers Union of South Australia, which found that the largest 2 contributing factors to teacher workload outside of actually classroom teaching are lesson planning, where the average teacher will spend almost 10 hours a week preparing lessons, and then on average 5 hours a week marking. So the problem that I am particularly trying to address here is there a way that I can try and use different forms or neurosymbolic forms of artificial intelligence to potentially reduce the marking workload with some automation? And the reason why I think that it's really important that we do this is that teachers and schools are already searching this out. In Queensland, there is a company called Edexia, which was actually part of the Y Combinator program in the US, which is already working with 12 private schools in Brisbane to automatically grade essays. And basically what they're doing at the moment is more or less taking the essay, making sure that there's no student name on it, and then uploading it to ChatGPT to grade. So it's not particularly sophisticated. And I think that if we don't make some sort of effort to try and make sure that grading is done, I guess, in an ethical and reliable way, then teachers are going to find it, or schools are going to sign up for it. And so that's kind of the motivation behind my research, is to try and have more reliable, explainable, and I guess grading that can also protect student privacy. So in particular though, rather than trying to grade absolutely everything, I'm focusing on physics. So I have a background as a physics teacher myself, and I actually I'm the director of the Australian Physics Olympiad program. And so I guess physics marking is something I've spent a lot of time in my life doing, and I'm very motivated to try and see if it can be automated. And physics exams, I think, are particularly interesting to try and automate because there are so many different types of questions that you can get on physics exams. So you can have short answer questions where students need to explain something. You can have diagrams where students have to draw a diagram of a physical situation. You can have students have to plot data and plot data points correctly. You can have numerical answers or algebraic expressions. And so if you can grade physics exams, that would, I imagine, carry over to a lot of other types of grading. Not essays, but many other types of grading would be covered by this as well. So what I just want to show you here is 2 examples of different types of responses. So sometimes there are exam responses which are typed by students. And so it might look a bit like this. This is a combination of algebra and a short answer question. Or this might be another example of a handwritten student response that includes a diagram, it includes some words, and it includes some equations. And we want to be able to take in all of that and process it. So that's the introduction phase of the talk. So the next thing I want to do is go through literature review of automated grading. And I think this will be the most controversial part of the talk, actually. So I hope that you find it interesting. So you'll see why in a minute. So basically, for my literature review, I tried to be systematic, and I searched a number of databases with different terms. I kind of broke my search into 3 main areas. So the first one is that I picked 3 databases which were particularly focused on, I guess, education, and searched many possible terms for finding papers, and we got 250 papers from that. Then I tried a broader range of databases, and then but a narrower set of terms, so it's just automated marking and education. And then I did a discipline-specific one where I went back to the education databases, but rather than searching for education, I just said physics and automated grading, and that returned another 78 papers. So that means that I had more than 2,000 papers to read, and I figured that if I did nothing but read papers, this would take many months to try and get through these all. So this is where it's controversial. I thought, can LLMs help with this process of screening all the papers? And so this is what I tried. I tried 5 different large language models. One is closed source, that's GPT-4o, and then 4 open source ones. They're all variants of Llama. So Llama is Meta's, I guess, large language model series. And I tried them in different sizes. So 405 billion parameters. This is essentially the largest model that was available open source at the time. 70 billion parameters, which is just small enough that you can run it on a local machine, essentially, if you want to. And then I tried some much smaller models, 8 billion and 3 billion, to see how they go. And then going from the very large number of papers from here to here, I just asked the large language model, so they have large enough context that you can actually just extract all of the text out of the PDF and give it to the large language model directly. So I did this, and then just asked it to classify each paper according to 3 criteria. Is it peer-reviewed? Is it about automated marking? Because a lot of automated grading is actually medicine. I think if you have some sort of wound, they grade the wounds about how severe they are or something like this. And so a lot of the papers that showed up were about that. And then the other thing I asked is the paper actually about a technological solution, or is it kind of more sociological in nature? And so I just asked them to classify all of the 2,000 papers according to these criteria. And I originally did it with all 5 of the models. For the first 958 papers, I got 100% agreement for the best 3 models, GPT-4o, 405b, and 70b, all agreed exactly about whether or not the paper was peer-reviewed, automated marking, or sociological or technological. So after that, I just started using, I can't remember, I think it was Llama 405b because it was cheaper, but slightly better than this. And so I used that to do the remaining of the papers. And from that, I essentially used that to screen and get down to 679 papers that would be that could be used for to check in more detail. I just thought I'd mention, because you might find it interesting in case you ever want to automate large language model, use large language models to automate literature review. The smaller models, their correlation with these 3 was weak. So 0.36 and 0.26. So I'd say these models were not necessarily smart enough to accurately determine these 3 things about all of the papers. Then the next stage after that was and this helped me get from this stage to this stage. With the 600 papers, I took the models and then I asked it to classify for each type of, for each paper, what type of questions is it looking at automating grading, and what technique is it using to grade. So the results from that are more or less here. So if you look at all the different possible question types, these were the categories that I came up with and their definitions. So we have algebra, code, diagrams, essays, multiple choice numerical answers, plots, short answer, and some papers were summary papers. So if we have a look, I didn't anticipate this, but nearly half the papers were actually coding, how to automate the grading of coding. I didn't expect that, but that's what came up. And then we also had a very large chunk of papers, 16%, that were for evaluating essays. This isn't so relevant to physics marking, so I didn't consider these papers, and that's more than 50% of them. The other thing is that there were different methods that were used for automated grading. So I've got all the definitions of the different types just here. But what I found most interesting was actually the trends if you look at this automated grading over time. So I've created a plot of what are the different automated grading, so the types of questions that are being graded and what are the techniques being graded. And one of the trends that doesn't surprise me at all is going from 2023 to 2024, we have a massive jump in the number of large language models that are being used for automated grading. And the other trend that seems to happen is essay grading has significantly, there's been a lot more papers about essay grading in recent years, is another trend as well. But I was only interested in looking at, there's one other thing I thought I'd mention. There's a somewhat correlation between the types of questions that are being graded and the way that they are being graded. So for code, unexpectedly, most papers are using test cases to try and grade the papers. For essays, they're mostly using text analysis methods. But I'm actually mostly interested in algebra, diagrams, essays, sorry, not essays, numerical, plots, and short answer. So those are the papers that I looked into in more detail to see what was going on. I won't do the full what I found in every category because the talk will go too long, but the most relevant and recent papers that were about grading physics exams came up with these three most common problems. So hallucinations of the LLMs that they were using, errors in the mathematical reasoning when they were using large language models, and they also raised some of the ethical concerns that I did before about uploading a whole bunch of student data to ChatGPT. So I guess the solution that I'm looking at or been developing is what I call alpha physics, I guess inspired by Google's AlphaGo, but also alpha geometry, which is it wasn't actually for marking geometry problems, but it was for trying to prove geometry theorems. And recently they've also been doing more general kind of alpha proof, which is for proving mathematical or answering Olympiad maths questions. So this one's actually focused on grading, but the basic idea is that you input a student response and a marking scheme, and then we start with essentially a neural network or a large language model phase, which will take student answers and to try and extract features from it. So we're not actually using a large language model for reasoning, mathematical reasoning or anything else. We're just using it as feature extraction. And then we'll have some sort of a symbolic representation. So for example, maybe it extracts this equation and then writes it like this. And then we try to use a symbolic reasoning engine, which can have some, I guess, guarantees on correctness to generate a final score. So this is the overall kind of pipeline that I've been working on. And so now I'm going to take us through the different components. So we've got the LLM pre-processing. I've been working on a computer algebra system specifically designed for physics. And then I've also been working on an explainable machine learning algorithm as the final part of the pipeline. Any questions about any of that so far?
How accurate was the LLMs for parsing? Did you find that? Did you do any rigorous testing?
Where for parsing, do you mean in literature review, or do you mean?
Oh no, just that previous page that you had, the previous slide. Yeah.
Look, that's exactly what I'm about to talk about now. So great question. Let's dive into it, Sylvie. Yep.
Maybe two questions, but I don't know whether it's not going to break the flow. So back in the 1990s, 2000s, there was a lot of work on student modeling in the AI community, where they were, in particular, using, I don't know that they were using physics, right?
Yeah.
But math definitely was there.
Yeah.
Trying to understand the ability of the student, propose new exercises and learning curriculum that they could do.
Yes.
They were using a lot of inductive logic programming, I remember. I don't know whether you think that's relevant and whether you came across that in your GPT-driven literature search.
So I would say that I have spoken to quite a few people about kind of this tutoring, I guess automated tutoring. But I guess that I see that really what I'm just trying to focus on is allocating grades. So I see there's lots of good things that you could have to help students with learning using AI. But I guess my focus is more specifically on just, can we grade these physics exams accurately? And that might feed into a bigger system that once you can grade accurately, then you can also recommend exercises for students, but that's a little bit beyond the scope of. So I am aware of it, but I haven't looked at it in great depth.
I suppose my second question is, when we talk about neurosymbolic AI, it's usually It's usually when you combine both and there is propagation of information, more like, gradient from the ML going and informing the reasoning or vice versa. But here it looks like it's quite separated, or did I misunderstand from?
I would say that you're right. It is really kind of two separate stages to the pipeline. The only thing is I will bring that back up right at the end, because when I do this explainable machine learning, I was trying to achieve something in particular, but it so happens that I did a paper on this and it got reviewed really, really well. And I didn't understand why, because it took a previous technique and made it end-to-end differentiable, where that wasn't possible before. So that was just a bonus that I accidentally stumbled across with this last step.
I was thinking,
but you're right, this is quite modular.
Okay.
Yeah. So I'm not trying to retrain the LLM based on any grading that it does. So I just don't have early on decided I don't really have the compute to train an LLM or even fine tune, and the LLMs are constantly getting better. So if I fine tune one, there'll also be a better one coming around anyway. So I want to see how well can I do with off the shelf open source LLMs. So I will make a comment about that since I'm about to go into LLM pre-processing, because I didn't put a slide on this. All the LLMs that I use in the pipeline are open source, so that way the process can be transparent. And there's designed to, I've been trying to focus on running things locally, so that way you don't actually have to upload your student data to anywhere. If you wanted to, you could keep it on the local machine to kind of address some privacy concerns. So hopefully that'll come through in this section here. So just to very quickly talk about LLM pre-processing, I did a kind of deep dive or a study on this particular question here. So I don't know if you've been in an airport and you've been on, they have these travelator things where you can walk faster by walking on the travelator. So imagine that you have somebody who is traveling with the group. Most of the group decided not to go on the travelator, but one friend does decide to go on the travelator. But then the group gets halfway and decides, oh, actually, we want to go the other way, and turns around. So now this person here has to quickly come back. And so the question is, how fast do they have to walk to arrive back at point A at exactly the same time as the group? That was the physics question. This talk isn't really about the physics question. It's about how do you grade the student responses to that question. So, just to show you the task that I'm actually assigning for the large language model, it is as follows. So a student might write something like this. This might be their response. And you can see it has a combination of text and equations in it. The LLM's job is to find the equations, so extract the equations, and then take them and return the equation in a formal syntax. The syntax is actually called SymPy, which is a package in Python specifically designed for computer algebra. The large language models know it quite well already, so it was very easy for them to return it in this format. You don't really have to teach them how the format goes. That would mean an equation like this looks like this in the SymPy format. So that's the task for the LLMs to do. These are the LLMs that I tried. So I tried different sizes of models. So there's 12 models altogether. Sorry, there is a 3 billion, which is missing off this table. There is 3, sorry about that. It looks like I have left 2 of my models off the table. I apologize for that. And so there's 6 different sizes, and then I did what are called thinking models and non-thinking models. If you're not familiar with the idea, in the early days of large language models, if you ask them a really long question, tell me blah, 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 tell me if it's true or false, then they would tend to just answer true or false, and that would be their entire answer. But the companies discovered they can increase the performance of their models by making them undergo a thinking stage first, where originally they would just do it was a prompting technique. It was called chain of thought, where you ask the model, think this through step by step, and by being more verbose, it would more likely end at the right answer. But then they just started making it so the model will inherently produce tokens that are hidden. So hidden tokens that are not meant to be intended for the user to see, and then it will give its final answer at the end. And so those models are called the thinking models. So these are the models that I tried. They're all open source. And I tried some different methods of prompting the LLMs. But I'd like to say they're a little bit more than just prompting engineering. So for the first method, you come up with the best prompt you can to try and get the large language model to extract the equations correctly. So I think I tried about 10 different prompts and landed on the one that was most accurate, to extract the responses from the students. That's what I call direct method. Then LLM modulo SymPy means that after you extract the equations, you try to run it through SymPy and check, does this actually match SymPy syntax or not? If it does, then great, you leave it alone. If it fails, then you send an error message back to the model and say, look, this is what you came up with, but when it is not syntactically correct, please try again. So that gives the model a chance to improve. Modulo Z3 is where I converted from SymPy syntax into Z3 syntax, just using a parser. And then Z3 was able to give more specific feedback to the model. So it might say there's a particular symbol that isn't defined. So once again, you just feed back to the model, but you're able to give it a more specific error message about what is wrong with its response. And then the consensus method takes the response from two different large language models. And then what I do is I check if these two equations that they've extracted, or lists of equations that they've extracted, are the same or not. If and I do that using Z3, which is a SMT solver. And if the two lists of equations are equivalent, then it accepts it. If they're different, then it goes back to both models and says, look, two different responses have been given. This is the original student response, which one is correct? And so it kind of gives them a chance to reach consensus together. If they don't reach consensus on 3 loops, it's the same with all of these. I give the model 3 attempts to try and fix. And then if it's still not correct by then for these cases, essentially it's going to fail, like there is no syntactically correct response. So the model has failed. If you get to here, then I just randomly choose one of the 2 models to accept the response from, if they still can't agree after 3 iterations. So those are the different techniques that I've tried.
Just on consensus, do you have time for a quick question?
Yeah, please do.
Like let's just say you've got 2 equations.
Yep.
At what point did you determine that they're the same thing?
Okay, so I chose to not include that in the talk, but basically I set up an algorithm that would go through every equation so each model produces a list of equations. So there's model 1 list and models 2 list. And then what you can do is you say, for the first equation on this one, check if any of these equations are essentially entailed by this one over here. And so I do that with Z3. And then if it is, then I click tick. And then I go to the next one and check if any of these.
Yeah, so what is the entailment?
Sorry?
What is the entailment in that case?
Okay, so the entailment in that case,
Like, I mean, is there some Z3 entails? I just need to look it up, or what is that?
So I actually wrote an algorithm for this, but Peter, do you want to interject?
Maybe so. I've given 2 equations over a signature that is known to Z3 because it comprises arithmetic, right? So times, plus, what have you, and a little bit of sine, cosine, but Z3 is a little bit opaque on what it has really implemented, but at least it understands most of the symbols that are in these equations, and its first order equivalence modulo some incomplete background theory that is implemented in Z3. So Z3 is used as a first order view improver modulo these arithmetic background theories as far as they are built into Z3.
Can I maybe just say, so I think, Charles, this is a really good question. I didn't put it on the slide, but immediately after the talk, can I just show you the exact algorithm that I used to do entailment? And yeah, that might be easier than trying to describe it now. Yeah. So yeah, thanks for the question.
Okay, so another question.
Yes.
So I think what have been discussed is more on the equation level, like whether 2 equations or 2 sets of equations are equivalent.
Yep.
But when we do marking, actually we've seen some students, they just have creative approach of setting variables. They may give you an entirely different equation system where the variables means something else.
That's right.
So is that covered in your talk? Or?
You're right. So basically, this is a really important point. So, and I think that I didn't emphasize it that much earlier on. But when you're going from here to here, the LLM is actually told, these are the variables that are expected in this problem. So there's the mass of this first thing, there's the mass of this second thing, there's this velocity. if the student has used different variables, redefine it in terms of these given variables. And so, for example, for this error message that I used here, symbol U is undefined. So a student might have written U, but symbol capital U wasn't defined. And so the LLM has to go back and look at the list and try and make it only in terms of the defined symbols. But this is actually a really important thing. We are asking the LLM to have the nuance of a grader of being able to distinguish what did the student mean in terms of this set of variables when they wrote this equation. So we are actually asking, we're outsourcing that to the LLM to do that for us. So yeah, so it's actually quite a difficult task. It's non-trivial, in my opinion.
Yeah, I would imagine that's difficult.
It's also, if I just go to my next slide as well, so I'll just quickly talk about, these are the different evaluation techniques that I use. The last one is called accuracy. And in order, you had to get every single one of the 12 equations correct for it to count as towards the accuracy. If you got just a single one wrong, it counts as 0 towards the accuracy for that particular case. So it is quite a difficult task. So it's only seeing, did the LLM get all of the equations perfect? And accuracy was determined by a team of the Olympiad markers actually sat down and agreed these are exactly what the student intended to write. And there were actually 7 cases out of 200 where the Olympiad markers could not actually agree. And so we call those cases ambiguous, and we don't expect the LLM to be able to get those correct because the markers themselves couldn't agree. But the other ones, we're taking what the markers said were the equations. Then I also took the time that it took to run, and then the number of tokens that the models generated.
Just want to ask, so the questions that you said about the Olympia level, so are they Olympia level questions or more like a school questions?
So they're Australian Physics Olympiad level, which is a bit of a step down from International Physics Olympiad level. So I would say this roughly corresponds to high school level, or it's a bit advanced for high school level physics, but on the advanced end, there's no calculus, for example. So I'd say it's pre-university. Yeah.
So I asked this because I think for IVO, they actually have something like experimental design that is a little bit like essay.
So you're correct that there is an experimental exam in the International Physics Olympiad. It's not exactly graded as an essay though. It really is, you have to play with some equipment and measure property X, like how much, like what's the elastic constant of this piece of something you've been given.
It's
so it's still quite numerically based, but you're right, we're not considering an experimental exam question here. Yeah. So this is the results. So it's essentially for each of the different models going across, I've included what their size in billions of parameters across the top. And then I've only recorded time for models that I was able to run locally. So because for the larger models, I had to send them off to essentially the CSIRO has a subscription with Microsoft Azure. And I don't know the GPUs that the models were running on in that particular case. And the amount of time that it takes to run, wall time, isn't really comparable. All of the smaller models will run on a local machine. And so that time could actually be indicating something useful in those particular cases. This is the number of tokens that the model had to generate to answer. So this is all 200 questions. So this is the time for all 200 questions to be graded. And this is the number of tokens for the direct method. And then this is the correct answers out of 200. Then if you add in the LLM modulo simpli, where it gets some feedback about whether its answer is syntactically correct or not, to be honest, there is not a big difference at all. I think this one improved a bit, but otherwise they're pretty much all the same. I'd note that that's very different to if you actually tell it what is syntactically wrong, which is what's given by these numbers here, then you actually notice a bigger improvement across the board because then they realize what the actual syntax error is. And then consensus is this, this line here, which for smaller models had a bigger effect than for larger models. To help us see this trend, I've actually plotted it as 2 different graphs. So the first one here is, if we just look at model size and accuracy, so model size on the x-axis, accuracy on the y-axis, and then we have our different techniques here. So direct method is in green, LLM modulo is in pink, and accuracy is in and consensus is in purple. And then I've used the dots here correspond to the thinking models that go away and think and then give you an answer, compared to the non-thinking models are marked with X's. And then you could very roughly kind of fit, there's a sigmoid pattern here that, as the model gets larger, you get higher and higher accuracy. The maximum that we could possibly expect was this 193 out of 200, because the graders themselves couldn't actually agree on this last bit here. So if the human graders don't agree, then we're not going to expect the LLM to get past that. And we do notice that there is an improvement for consensus at the upper end, and LLM modulo is generally improve the performance. But when you look at it from a different point of view in terms of the actual runtime, so this is for the smaller models that could be run locally. This is the amount of time that they spent on a logarithmic scale down the bottom here, and here's the accuracy. This paints a different picture about how useful consensus is. Because for these models, even though consensus might have technically been more accurate, because it cost more time, overall, it didn't really appear to be worth it. I just made note that these ones all up here are actually Microsoft's model 5.4, which I hadn't heard of until I actually tried it in this experiment. And then I put here a practical time limit. This is a rough estimate for normally the physics Olympiad marking has to be done on a single weekend. But you could blow that out to 2 weeks if you wanted to. But there's actually 15 graders who all meet in the physics building and they just sit there and do nothing but eat snacks and mark for an entire weekend. If you wanted to achieve the same thing with just one of these computers that I was using, and you wanted to grade all of the responses to all of the exam questions, you would need to be spending no more than approximately 4,000 seconds per 200 student responses, essentially, to be able to get through the entire thing in time. Now, of course, you could scale that up by a factor of 10 by just adding 10 computers, and you could scale that up by a factor of 10 again by giving them 2 weeks. But this was just a very rough, approximately what is like feasible for running locally to achieve this task. And so it's about here. Maybe these ones are okay. You're probably not going to be able to use those ones, though. It's just too expensive, computationally expensive to work. So, yes, Patrick.
This may be a
Slide
side question,
Okay.
but I'm just wondering, what's the relevance of number of tokens generated? Like, why do we care? Why is that an interesting thing to measure?
Yeah, so I would say that number of tokens is just another potential method for measuring the computational expense of running the large language model. Potentially, you could say it's more accurate than using the wall time. And it means that I could actually compare the larger models. These ones that I couldn't run locally to these other ones for how much compute they're actually using to run their answers. So that's, I guess, why you would do it. Yep. There is a massive difference between thinking and non-thinking models. If you have a look, like this is more than 10 times as many tokens, so 10 times as expensive to run. So, yep. Okay, so then I also had a look at what the different errors were that the different models were making. And I looked at this manually for the largest models here. So all up for the largest models in their consensus responses, there was a total of 24 errors, and it was possible that there was more than one error in a single student response. So there were 24 student responses that they didn't get correct. And in those, I was able to find the following errors. This one I thought was the most interesting. This is essentially hallucination, but sometimes the students wrote, I see an attachment for the equation. And no attachment was provided to these models. They're not vision models. They can't actually see. And we didn't provide. So the students actually did legitimately have attachments that were graded by the graders. And so we took these ones like out and said that the score should be assigned 0 because there's nothing there to grade. But large language models would be essentially prompted to start hallucinating equations. And so this was the most common error from the best models, was that when it says there's an attachment here, please read the attachment, it would start hallucinating these, and it would even arrive at consensus on what the hallucinated equations were after a while. So I think that kind of is a warning sign for us about how accurate these things can get and how dangerous hallucinations are. And then the other errors were if it's using an undefined symbol. So like I said, the students might use the wrong symbols, and you need to translate that into the standard set of symbols for automated reasoning. So if the large language model didn't do that, then that was these errors here. Just missing an equation out of the list or adding an extra equation, and then incorrectly interpreting what the student meant when they wrote an equation. So for example, maybe a student left off some brackets somewhere, but a grader would have been able to look at it and say the student meant to write this, whereas the LLM in 2 cases missed that. Now, afterwards, I realized that it was possible to automate the first 4 error types. So I did that for all of the different sizes of models. I didn't bother, well, I did actually do it for the smaller ones, but there are so many errors that they're all like 100, 100, 100, stopped being interesting. Yeah, I also automated the first ones. It was not possible to automate the last one, so I didn't do it for the hundreds of responses for the smaller models. So those are the most likely errors. So just to very quickly conclude this first part, sorry, I know this talk is really going to go on too long. Really sorry about that, everyone. I might just be giving a talk about LLM pre-processing and then quickly saying everything else afterwards. The LLM modulo framework was probably the most effective for LLMs, but only if you give them specific feedback on where they've gone wrong. And then consensus between models worked best for, it didn't help the largest models very much. 5.4 was the model that showed the most promise in this particular experiment, giving a trade-off of time and accuracy. And the maximum accuracy that we could attain was 88% compared to markers, human graders who could agree at the 97% level. Okay, so I'm aware that I'm only halfway through the talk and time's nearly up, so I guess I'll just try to speed run the last bit. Sorry about this, everyone. I should have managed my time better. So if we look at computer, the next thing I was looking at is, okay, once we have these extracted equations, what can we do with them? So we might now have an LLM extracted equation like this, and we need to see, is this equivalent to something in the marking scheme like this? And they look really different because they're in different variables. So is there a way that we can kind of make them look the same and check, are they actually equivalent? And so I guess up to this point, I've been using Z3, but I've moved on to more difficult questions for this part, where Z3 essentially is incomplete and unable to determine if equations are equivalent. So I'm now looking at the reasoning engine part of the pipeline. So
just a quick question. Is
Yep.
Z3 a totally LLM system, or is a mix of LLMs?
Oh,
or
no.
Some of the classical symbolic techniques.
Sorry, Z3 is completely symbolic. There's no LLM component at all. Yep, so it's a satisfiability modulo theory solver. So basically it tries to, you give it a query and it tries to say if the query is true or false, and then you can give it some background mathematical knowledge that it can use to try and prove that query as sat or unsat.
Yeah, I asked it because I remember Z3 series follow us, have something like LLM or Z3.
Oh yeah, so that meant when I said modulo Z3, that essentially means the LLM receiving feedback from Z3. That's, yeah, maybe that name isn't so helpful for people who aren't in the SMT field. So, so the first thing to do was essentially, I'll just try to go through this quickly so we can get through the talk. So there were some substitutions we need to make. So all of the marking scheme and student responses are given in terms of final variables, which can then be solved. So, whoops daisy. So, okay, what I just wanted to quickly say about this is the reason why I'm trying something here rather than using Z3 is that trigonometry is very important in some physics problems. This here is one of the physics problems on the exam, and therefore I wanted to develop a system that would be able to handle trigonometric functions. And so this is going to potentially take a little while to go through. So, all right, I'll just very quickly do this. So the problem is once you add transcendental functions, for example, including the trig functions, is that in 1968, Daniel Richardson was able to show that if you have a language that can express pi, e to the power of x, and sine of x, then there's no algorithm that can generally show if such an equation can be solved or not, or if, in this case, we're defining it as if you were given an arbitrary expression in this language, is that equivalent to 0 everywhere or not? So, and so that essentially means that there's going to be no way that if you want both exponentiation and trigonometric functions, both of which are useful in physics exams, there's no way you can have a complete system that will arrive at this is definitely equivalent or this is definitely not equivalent. So I chose to carve out and try and just look at trigonometric problems. So I throw away exponentiation by variables and only allow exponentiation by integers in the hope that I could come up with a system that would be complete in that area. So, okay, so this is, I guess, kind of preliminaries. I might just point out some key points from this, but not go through all of it. So basically, I set up a signature or a language which has got some symbols in it which correspond to physical quantities that I call parameters. It also has constants that refer to the essentially floating point representations of real numbers and the integers. And then we have only these specific symbols, and there are some caveats on them. So exponentiation is only allowed for positive integers. And we also have some restrictions about what the arguments of sine and cosine are allowed to be. And then there's one other symbol here that I have called quote. And quote is a function symbol that basically says that whatever is wrapped inside it acts as is an actual placeholder for a real number. So either an integer or a floating point representation of a real. And this is very important for when you're trying to prove properties about the system that you have this operator. So, okay, so then I'm saying that a rewrite rule more or less is a pair, which I tend to write as the left-hand side goes to right-hand side, where both of these belong to the signature with variables. Yeah, I'll just keep moving because I'm out of time. So I've got some more preliminaries here that I might just go through. Sorry about this, everyone. But basically, we just want to, the purpose of our TRS or term rewriting system is that we want to, maybe I've skipped over a little bit too much. Okay. Basically, the idea is you want to have a set of rules. So something like this, where if you see something on the left-hand side, you can rewrite it to something different on the right-hand side. And then you just keep applying rules again and again and again and again until you get to a point where you can't go any further. And we call that the normal form. So I'm representing normal form by this symbol here. So this means normal form of T. And the idea is if the system is one, terminating, so it eventually ends, you don't have any infinite cycles, and two, if it's what we call confluent. So that means that there's only one normal form for each term. Then we are essentially using joinability here as our way of checking syntactic equivalence of two algebraic expressions. So if you have one expression and you have another expression, if they have the same normal form, then we're saying that they're joinable and that they are algebraically equivalent. So that's the overall game that I'm trying to play here. And then, yeah, and so for this to work, we need the system to be terminating and confluent. I'll just very quickly say there are a lot of different rewrite rules that I have. So there are some basic associative and commutativity based axioms that I've got here for addition and multiplication. To avoid infinite cycles, you need to add what we call guards or constraints to the rule. So it means only apply this rule if x is greater than y. According to, we have a way, so essentially I call it a vector metric or a weight that determines how large is this term compared to this term, and then you can know whether or not you want to apply your rewrite rule or not. We have distributivity rules and we have some rules for exponentiation. Then on top of that, we also have rules specifically about quote terms. So these are standing in for actual numbers. So if you have 2 plus 3, then you can just call Python to evaluate that and give you a new quote term. So that's part of the system, and we have it for multiplication and for exponentiation and for subtraction. Then I also have identities. So this essentially means some sort of simplification that can take place. And then I also have these trigonometric rules. So these can be used to simplify trigonometry-based expressions, and this is where we essentially have an advantage over what Z3 can do. So I took so it's 1,526 student responses, and I tested them with a few different systems. So the first one is I tried with Z3, and I gave it some trigonometric axioms, some basic ones, essentially more or less equivalent to what I gave the term rewriting system. But the problem is it would get stuck and it would fail in many cases. So it wasn't able to determine SAT or unsat. However, if I was more intelligent about, okay, Z3 is an SMT solver, rather than giving it the raw axioms, let's give it a few tactics that it can use to try and solve these. I was able to increase its performance. It would operate very quickly and it would fail far less often. Then we created 2 term rewriting systems. The first one kind of had 4 different steps, and then the other one is the one I've just shown you now, which only has kind of one component to it. And in these cases, we were able to get down, like it was able to find the same normal form in every single case, and it worked. So that was showing that the term rewriting system is very useful for this physics grading. However, there are some open questions about it. I have yet to actually prove that it is actually terminating and prove that it is actually confluent. It was terminating enough and confluent enough that it worked in this case, but I haven't proven it in general, and I'm still trying to prove that at the moment. So
But all the Australian pieces of Olympiad questions are terminated.
So actually, I don't even know for all of the questions. I only know for these 2 questions, question 25 and 26, that it worked. So, and I can tell you that because this one is optimized for trigonometry, it doesn't work well for exponentiation, and it would definitely fail on another question which requires exponentiation by variables. So, yeah, so this is very narrow. Unfortunately, it is not possible to make a system that can definitely solve everything. You're right. It does eventually tie back to the whole problem. So, yeah. Okay. I'm just going to quickly speed run through to get through this last part. So the last part was I have an explainable machine learning component that I put on the end. And the reason is essentially marking schemes are not always black and white. Sometimes markers need to be able to interpret a student, like a marking scheme, and say, look, what a student wrote is this, and technically it's not the same as this, but it's close enough, and I'll give the point anyway. And so basically, if we look at the stages we've looked at so far, we have a first step, which will take a student response. It can extract equations, but also things like text and properties of diagrams. And then we then have a set of equations. We have some text and we have a marking scheme. And the question is, my battery is running low on the computer. Sorry, guys. I'll talk and plug in my computer at the same time. So the question is, how do we assign a grade based on all of these features? And we could just use the marking scheme directly in a symbolic way. Or what we could do is, if we have some marked examples already, we could try and learn from the marked examples and therefore like try to imitate what a grader would do and be more nuanced. And so this is what I looked at for this part here. So there was an existing algorithm before I started my PhD called FOLD, which is called First Order Learner of Default. And what it does is it generates logic programs based on a table of data, input data. And a lot of work had been done on it in the years kind of leading up to my PhD. So it was actually competitive with some ML tools such as XGBoost on some data sets. So I was going to give an example of the Titanic here, just to very quickly show what a logic program is. But basically the idea is that it would look at data like this about all the passengers on the Titanic, what's their gender, what's their age, and then it would come up with rules that predict whether or not they survived. And so here's an example. It's got 2 rules. It says that if you are, in this case, so you survived is false. So you perished if you were not female. And then it comes up with the second rule, which says if it's not rule 1 and if it is rule 2. So if you are female, then you survived. And this is the rule that it came up with. It so happens this rule is pretty good. but it's not actually perfect. And I wanted to verify this. So I actually went to the Titanic data set and found, wait a minute, this isn't always true. So I actually implemented, so I upgraded fold to what I call confold, which adds confidence scores to each of the rules. So now the rules look a bit more like this. They have the extra confidence scores. And so it happens that if you're a male on the Titanic, you only died with 90% confidence or confidence calculated by this formula here, which essentially in the limit of large numbers of samples in the table becomes probability. And if you're a woman, that you 97% of the time survived, which is pretty good for the women. There was one other change that I made. It's a little bit subtle, so I might leave it alone given the time constraint. Then the other thing I did is once we had confidence scores, this is actually where we come back to the end-to-end differentiability. So people are already connecting neural networks in to be able to give inputs to these algorithms. But now, because it produces something that rather than just giving a 1 or a 0 at the end, instead it produces a number, it's actually able to be end-to-end differentiable. So that's where it tied back into Sylvie's question. But the other thing that you can do with these confidence scores is you can add pruning. So I added some pruning algorithms to it. I won't go in detail into the pruning algorithms. Sorry about that. But basically, this is, if you try and prune, I've created this graph. There's a lot of information going on at once. The color indicates how accurate you are. And if there's a black dot in the middle, that means you are more accurate than no pruning at all. And then if you're very, very red, that means that it is very, very low accuracy. So if you prune really harshly, then you end up with essentially the accuracy is very poor. And then the size of the dot indicates how many rules were left over. So originally we might come up with 60 rules or something like this. That's no good for humans, right? It's not very explainable if I have to read 60 rules to figure out if I died or survived on the Titanic, or if I get a point or not on the physics question. So we want the rule set to be as small as possible. So we want these circles to be as small as possible. So circles like this are pretty good. We're beating the accuracy without pruning because we're preventing overfitting. And we're reducing the rule set so it becomes more human interpretable. And then basically how this ties into the bigger picture is that you could then generate a set of rules that would then be used to automatically grade the student responses. Based on these responses I've already read, this is what I should do to allocate the new response, points to the new response. So I tested this on some standard benchmarks here. I might just keep going for now. Sorry about that. I also invented a new metric for probability-based predictions that has some nice properties. And then this is when I actually, this isn't for the physics grading. Sorry guys, I didn't include a graph for the physics grading. This is for a standard benchmark, but the same pattern held for physics grading as well. The algorithm was able to learn from very small amounts of training data compared to XGBoost, a more traditional machine learning method. The reason why that's particularly handy for physics grading is means you don't have to grade several hundred responses to get an okay improvement to just using the straight out marking scheme. So yeah, so what was really nice about this is it was able to learn a lot in the low data regime. So yeah, so these are the overall conclusions from that part of my work. So it was able to, Confold was able to improve and it added confidence, which is good because you can report that to the students as well. We're 97% sure that your grade should be X. I introduced this new metric, and then pruning was able to be introduced based on the confidence scores, and that could improve performance in some cases. And in the low data regime, we're outperforming XGBoost. So to wrap up quickly, this is the kind of pipeline that I'm working towards. Each of the individual components has now been tested on some physics problems. But what I'd really like to do next is actually pull all of the components together and actually try and grade an entire physics exam and see how well does the pipeline hold together.